So today we're going to be able to define what a rate is, and then we're also going to be able to determine if a set of values is a rate. Now this is not all that's really going into this. This is where we start to link a lot of the pieces together, and this is where we start to take some of the ideas from last year and some of the ideas from this year and some ideas that you have from science, and we're going to start piecing them all together. All right? So if you have a good understanding of those things, this should all start to loom together, and it should all start to make sense. You have to engage your brain, though, in what's going on. All right, so what is a rate? A rate is a relationship between two things in which one changes based on the other. So what we're talking about here are instances where one thing changes and that forces another thing to change. And a lot of times we're talking about variables here. So one variable may change and it causes the other to change. Somebody with a raised hand. What rates do you already know about? Name something that's a rate. One thing changes and another thing does. So Mason has come up with this rate that he knows about. We're talking about the dollars that he gets for each chore, or some relationship between the amount of money that he gets and the number of chores he does. Now, we can also take this back to science. Coming down here, talking about science. You've talked about this before. You've talked about dependent and independent variables, right? All right, so when we're talking about rates, we're always talking about the dependent variable as being our y value. And our x value is our independent variable. Remember when you talked about it in science, you said, all right, if I'm going to plot my two variables, you're always going to put the independent variable on which axis? The x-axis. So when we start to think about this makes sense. This is our independent variable. And so if we start to think about how we might start graphing this instance that Mason has come up with, chores would be on the x and dollars would be on the y. We'll explore that a little bit more in a second. Any other ideas about other possible rates? Callie? Grades. What about your grades?
The more, the better you do, the more assignments you do, the higher grade you get.
I'm going to save that one. I think there's a relationship there. I don't think that's quite as exact as a rate would assume, nor do I think it's necessarily a constant rate, but I like where you're going. Sammy?
The more money you pay, the more gas you get.
So he's talking about the number of dollars versus the number of gallons of gas. This is one that people see all the time. People are constantly using this particular rate to calculate how much gas that they can get with the amount of money that they have. Any other rates you know about? Jacob, I thought you had your hand up.
I did, but then after what
What would you have to say? Tell us. Let's talk about it.
the more you eat,
The more you eat what? The what? The heavier you get. So we can probably take that more exactly, like the more, if we were more exact, like the number of calories the number of donuts you eat relates to the number of calories that you eat. Okay. Other ones you might know? Simple. Miles per hour. A very common one in cars. Sammy was very close to this one. The number of miles you can get on the number of gallons of gas that you have in your car. There are other rates, thinking about temperature, the number of degrees that the temperature is changing over time. Callie.
like a clock, like on each time, I mean, or something like that, but like per minute, like say like a cheetah, it could run like something miles per hour. I mean, minute.
Yeah, so changing any of these rates into different units where they're measuring the same thing, but we're just using different units. We could say feet per second, meters per second, feet per hour. You know, any of these things, they can be different measures. These are all rates. Okay? And what we're talking about today is we're talking about constant rates. Rates that stay constant throughout the entire time. Now, so the question is, how would we know if something is at a constant rate? How do we know if something's speed is a constant speed or a constant rate? Terrence.
It has a pattern.
It has a pattern. Tell me more.
So when it has x is 1, then y is 2. So the next one, when it is 2, there's 2 more of the y, so then the x goes up 1, and then when it goes up another, it has another 2.
Perfect. So what I'm hearing him say, and I'm just going to summarize what he said, is that it changes, the y changes the same amount for each x. The y changes the same amount for each x. So what we can see down here is that we have our x is changing 1 and our x is changing 1. So this is going to tell us how much it's changing for each x because we are only moving 1x. How much is this changing? Y, okay, is a positive 2 and a positive 2. So what we can see here is that this does appear to be a constant rate. If it was a constant rate, what would my value be for 4? Changing 1 more, my constant would tell me I would need to change 2 more, so I heard somebody say 8. And we could keep continuing this pattern over and over and over again. And so what we see is the relationship here is going to be something that we can repeat over and over again. And actually, I could go backwards. If I had 0, what would my y be? I would have to go backwards to 0. If my x was negative 1, I have to go backwards 2 more. Negative 2, and so on and so forth. And so we can represent this entire rate by graphing it. What shape, here in quotation marks, do you think the graph of a rate is going to make? Tell your partner what you think. All right, let's just find out. Let's plug this in. This is where we have to remember our graphing skills from last year. Make sure that you have your graphing skills down. The x tells us how far we are moving left and right. So this tells me I'm starting here at the origin. I'm moving over 1 and up 2. And I'm going to go ahead and label that point for now, just so we are not forgetting here. So this is point 1, 2. And my next point is 2, 4, so that's over 2 and up 4. 2, 4. And over 3 and up 6 is 3, 6. And sure enough, if I take a straight edge and I line this up, I heard most of you predict that this was going to be a straight line. And you should use a straight edge, because if you don't use a straight edge, you're going to find yourself bending. That's a much straighter line. You're going to find yourself bending your line to make it fit. And if it doesn't make a line, is it a constant rate? No, that will tell you that at some point it changed too much or it changed too little in 1 unit, if it's not a straight line. And that's actually one way that we are going to be testing whether or not something or a set of values represents a constant rate, is to be able to graph it. That's one way. The other way we can talk about it is by looking at it this way. My ratio of change. This was my change in my y, my change in my x. It's a 1-to-2 ratio. This is a 1-to-2 ratio. This is a 1-to-2 ratio. So we can see that that ratio is the same all the way throughout. It's constant. My change in y is the same as my change in x. All right, so you guys already knew what the next value would be. Let's come up here. What could the x and y stand for? So this is where we're going to take this problem that had no context, and we're going to create a little bit of context for it. Looking at the x and y values down here, what could this have stood for? What could this have represented in the real world? What could this problem have been in the real world? What could x and y have been in the real world? What could the possible meaning be? Katarina.
For x?
Both.
Maybe like x means time,
Mm-hmm.
and y like how much?
How much what? Time is always a great independent variable, and you can almost pair anything with it with no context. What can happen over time at the same rate? Anything, like what? This could represent the number of gallons of water that you are drinking. And she said time. What are your units of time? Minutes, hours, seconds? Hours. Okay, so the number of gallons of water that you drink in an hour. This would be rather impressive feat. So she's saying the x would be her amount of time, which she's saying is hours. And y would be the number of gallons of water, gallons of H2O drunk. I don't know. One of those versions of drink. All right. I'm no expert on grammar here. All right. So, using what you've just said above, what is the rate in this situation? So what is the rate that water is being consumed? I should have said consumed instead of the drink. All right. What is the rate that water is being consumed here? What is the unit rate with the numbers? Mason. All right, so he says our rate is 2 gallons for 1 hour. And we recognize we could have pulled that right from down here. We were changing our y is 2 gallons over 1 hour. So we can see that our rate is the same thing as our change in our y, or our change in our dependent variable over our change in our x, or our independent variable. Now, does anybody remember way back to last year at some point you talked about this idea right here, the change in y over change in x? Does anybody know what that stood for on a graph? Anybody remember that? Slope of a line. So what we can see here is that if we think about rates, rates graph a line, and the rate is equal to the slope of the line. All right? So we can see here that going back to this line, the slope of this line is, you probably learned it doing triangles. You have a rise of 2 and a run of 1. Change in y over change in x. All right? Now we'll dig a little bit more into that concept, but I just wanted to plant that seed about slope and rate moving forward. Now let's look at some of these other examples. This is where we're really going to get into the, can I find the slope of a line? Or can I find if a set of values represents a constant rate? That's the better question here. That's what we're doing today. All right, so let's look at this. There are 2 different ways we can really think about this. Before we start thinking about it either way, I want you to take a guess. Kip yes or kip no. Do you think that this set of values represents a constant rate? Kip yes or kip no. It's a guess. It's okay if you're wrong. If you don't know, just take a guess. What do you think? Lola, why do you say yes? Tell me more. You said it looked like it was adding. Well, now I see you starting to graph it. So this is one way we can figure it out. She's saying, you know what? I know that if this is going to be a constant rate, it has to have the same slope. It has to have that line all the way down. So she's saying one way I can prove this, Mr. Boots, is by graphing it. This is absolutely one way. So I'm going to graph 1, 3. That's over 1 and up 3. Over 2 and up 5. And over 4 and up 9. Now, I can see that Preston over here has the straight edge out, and he's ready to test whether this is a line or not. And sure enough, when we graph this with a straight edge, obviously I don't have a straight edge over here on my iPad, it does go through all 3 points without bending. So kip yes or kip no, knowing that we know that these points make a line, do these represent a constant rate? Kip yes or kip no? Kip yes or kip no? Do we know this makes a constant rate? So you're telling me it's a constant rate because it graphs a straight line, but I'm looking here and I'm like, well, it changed 2 and then it changed 4. What's wrong? I don't get it. It didn't seem to change it the same thing. One time it changed 2, one time it changed 4. Dahlia. Yeah, so she's looking over here and she's saying, well, here your change in x was 1, but here your change in x was 2, so it should be twice as much change. And so we look at the ratio, 1 over 2. We look at the ratio, 2 over 4. Are they the same? Absolutely. It has the same rate of change throughout. So kip yes, this is a constant rate, and we proved it 2 ways. 1, that the ratios between the change in y and change in x were the same. That's this work down here. And 2, We showed that the change in y over change in x remained the same by showing that I graphed a straight line. So there are two ways to prove it. Today you're going to make sure that you know how to do both. Because you know what? One will always check the other. Alright, so let's look at this next one. Kip yes or Kip no. Does this represent a constant rate? Does this second set of values represent a constant rate? And I look around and I see a lot of you not giving me an answer because you're actually getting into solving it. You're like, you know what, Mr. Boots, I don't want to just take a guess. I know how to do this now. Let me do it. All right? So take 30 seconds with your partner. Go ahead and do it. Edgar, why do you say yes?
Because if you graph it, it's gonna be straight, and then if you do the other way to prove it, it's gonna be 1, and then 2, and then the y is gonna be 2, and then plus 4.
All right, so he's just given me both ways. He graphed the points 1, 2, 2, 4, and 4, 8. He's graphed these 3 points and he says, yes, Mr. Boots, I checked with my straight edge. These make a straight line. And he also said that I have the same ratio here. 2 to 4 and 1 to 2 are all the same thing. So yes, these are indeed at a constant rate. All right, let's flip over to our together time. I'm getting mostly yeses. Somebody with a yes, tell me why. Monica, tell me why. Okay, so she says one thing is that she graphs a straight line. So over 2, down -2. Make sure that you have that graphed correctly. Over 2, down -2. Over 4, up 2. Over 5, up 4. And over 7, up 8. And if you get a straight edge, and it should go straight through. Somebody else, the other way. What's the other way? You have to be able to prove this both ways. Giselle. Yeah, so what's your change in x? 2, 1, and 2. And the change in the y associated with the first one is 4, then 2, then 4. And so I look at these ratios, 2 to 4, 1 to 2, 2 to 4. 1 to 2 is the same thing as 2 to 4. All right, so yes, this is a constant rate. What could the x and y stand for? What real world situation did you come up with? Mason.
How many sandwiches are made per second?
All right, sandwiches per second. That's fast. I will question though. I will question how you had worked for 2 seconds and you had -2 sandwiches. So I will suggest that your particular scenario doesn't work particularly well, doesn't fit particularly well because of the negative number here. What do we know that has negative numbers that we've worked with a lot already? Adrian. Temperature. So this could be the temperature change per hour, x and y. It could be x is the, let's say it's an hour, and y could be temperature. And the units for temperature are degrees Fahrenheit or degrees Celsius. So in this case, our rate would be the number of degrees Fahrenheit that it changes per hour. What's the rate with the numbers? What's the rate with the numbers? Aaliyah? So I heard you say that it's changing 2 degrees for 1 hour. It's that ratio right there. It's that rate. It's that slope. 2 degrees for 1 hour. All right. Next one. For 2 and 6, -2. And she got out her straight edge, and sure enough, it went through all points. What's interesting about this particular relationship? What's different about this relationship than all of the other ones? Drak? No. Edgar? Yeah, this is a decreasing relationship. All right? What's the other way that we could prove this? Jacob? Checking for the pattern. So, checking for those ratios. 1, 2, and 2. This is a change of 2. This is a change of 4, but these are negative changes. And a change of -4. So I see my relationship here. -4 over 2, -4 over 2, -2 over 1. -2 over 1 is the same thing as -4 over 2. So yes, this has the same ratio of change in my 2 units. What could X and Y stand for? Jasmine, what could X and Y stand for? What did you put? Laps left, because that number would actually be decreasing in the minutes that you have. All right. Using the answer above, now you all may have different units on this, but what's the rate? What is that change in y over that change in x? What's my dependent change over my independent change? What's my rate? What's my rate? What's my rate? So this is where it's super important that you need to have a straight edge. And I can see that I can draw a line through 3 of these points, but this one is not on the line. That is proof that this is not a constant rate. Kylie, you were getting ready to tell me, how else did you prove that this was not a constant rate?
The graph, and also to find the rate, didn't match.
Yeah, so he was trying to find the rate, and he found that the rate wasn't the same all the way throughout. This is a change of 3 and an increase of 4. This is an increase of 3 and an increase of 2. This is an increase of 3 and an increase of 3. So in fact, at no point is there an appropriate rate through all 3 of these points. I have 3 over 4, 3 over 2, and 2 over 3. 4/3 is not equal to 2/3, which is also not equal to 3/3. So no, this is not a constant rate. At some point in time, this rate sped up and slowed down. We'll talk more about speeding up and slowing down and what that means in a minute.